So we were looking at this bisimulation. So essentially, it's a binary relation over the states of the Kripke structure. You can consider them as states of the same Kripke structure or states of different Kripke structures. And as we say it, so the idea is that like two states are bisimilar if first of all their labels have to be the same set of propositions, atomic propositions that you satisfy. And then for every successor on one side, there has to be a successor on the other side so that they match, and vice versa. Like, so it's a two-way kind of a thing. And if you are particularly talking about Kripke structures that are bisimilar, then you have to talk about their initial states, right? For every initial state in one Kripke structure, there should exist a corresponding thing, state in the other initial state in the other Kripke structure, and so on, right? And it's the bisimulation was introduced by Park, and it was popularized by Robin Milner, who is a Turing laureate. Essentially, he used these to talk about or reason about various processes in something called process algebra. So there are different varieties of process algebra. So the one that Milner studied is called the CCS. CCS, Calculus for Communicating Systems. Okay. So in process algebra, essentially you look at different processes, how they evolve. And in every algebra, there are different kinds of operators, right? So here also you have, in process algebra, you have like operators which will keep processes in parallel or in sequence and things like that. Okay. And we also talked about the bisimilarity relation, which is the largest bisimulation relation. And this is an equivalence relation, right? So we mentioned. And so essentially, this relation, it's reflexive, symmetric, and transitive. We also talked about the path bisimulation or a string bisimulation. And we said that there are the two states, they are bisimilar if and only if there exists path bisimulation between them. Okay. And then we also looked at the game characterization of bisimulation. Like you can look at this as a game between two players, a challenger uh, and challenger or an attacker and the defender. Okay. So, and essentially how is the game played? Like, so you consider these two states. So the idea of the challenger is to prove that the two states are not bisimilar, whereas the defender wants to show that they are bisimilar. Okay. So the challenger chooses a side, makes a move, the defender has to sort of mimic the move. Okay. And if the game continues forever, like over infinitely many such rounds. So in every round, you start from a pair of states. The challenger makes a move and the defender responds. Then again, in the next, from the next configuration in the next round, the challenger chooses one of the sides. The defender has to choose the other side, and the game continues. Clear? So if it happens at some point of time, after a finite play, the defender cannot mimic the move of the challenger, then the defender loses, in which case we conclude that the two states that we started with, they're not bisimilar. Okay. Um, yeah. And we also mentioned that if there are two states which are bisimulation equivalent, then they are also trace equivalent, but the other direction may not hold. Like if there can be, for example, like we looked at examples that are that have Kripke structures that have the same set of traces, but they are not necessarily bisimulation equivalent, right? So, and you can also talk about quotienting with respect to a bisimulation in the sense that you find that there are sets of states which are bisimilar to each other, and then you can merge them and you can get a smaller, potentially smaller transition system. Okay. So the things which are in the same class, they are equivalent, bisimilar equivalent. You can expect similar behavior from the states. So you don't have to look at all the states separately, but you can just merge all of them and then from there you can evolve. Okay. Right. So, yeah. So this is the game characterization we already saw. And this is an example of uh, two Kripke structures which are trace equivalent, but they are not bisimulation equivalent. Right? They are not like the states here S and T, they are not bisimilar. Okay. And this theorem says that the states are strongly bisimilar, or yes, bisimilar, if and only if the defender has a winning strategy in the strong bisimulation game, starting from the configuration which has these two as the uh, initial states. Okay, right. So, and they are not strongly bisimilar if and only if the attacker of the challenger has a winning strategy. Good. So now what we are going to look at is essentially that if there are two states which are uh, strongly bisimilar, then they are CTL equivalent in the sense that they satisfy the same set of CTL formulas, and vice versa, in the sense that if they satisfy the same set of CTL formulas, then they are also bisimilar. Okay. So um, let's say that first we start with this direction where consider the set of states which satisfy the same set of CTL formulas. Okay, so this is how I denote this. That S1 with this equivalent with a CTL subscript S2. That means S1 and S2, they satisfy the same set of CTL formulas. And what we want to prove is that S1 and S2 are bisimilar. Okay. So indeed, if I construct such a relation, we want to show that R is a bisimulation relation. So we would like to prove by uh, contradiction. So what is the things? We would like to say that suppose um, um, it's like S1 and S2 satisfy the same set of CTL formula. Okay, let's let for by way of contradiction that by way of contradiction that S1 and S2 are not bisimilar. Okay. So if S1 and S2 are not bisimilar, then what happens? Like, so, or let's say, or I can say, stated other way, we can, what we are trying to show is that this relation R is a bisimulation relation. Okay. Or we can also say that R is not a bisimulation relation. So in that case, what happens? Like, so S1 has a successor, let's say S1 prime, and then it happens that all successors, for all successors S2 prime of S2, we have that uh, uh, S1 prime, S2 prime, it does not belong to R, right? Because since we are saying that this relation R is not a bisimulation relation, and so you have such a pair S1 comma S2 such that S1 has a successor S1 prime, but for all successors, they are you have such that uh, for all successors S2 prime of S2, you have S1 prime, S2 prime, they don't belong to R. Okay. Right. So in that case, what happens is like S1. So then if you consider a pair S1 prime, the pair S1 prime, you consider some successor S2 prime here of S2, then there exists some formula, some CTL formula, such that, let's say I call it some phi j, such that without loss of generality S1 prime satisfies this formula, but S2 prime does not satisfy the formula phi j. Clear? Right? So, uh, okay. So if it is not a bisimulation relation, then for there exists some successor S1 prime of S1, such that for all the successors S2 prime, they cannot match. Right? So S1 prime, S2 prime, they don't belong to the relation R. Okay. So now if that is the case, then by definition, there exists some formula, let's say I call it phi j, such that S1 prime satisfies phi j, but S2 prime does not satisfy phi j. Right? So, and this is for every successor S2 prime of uh, S2 prime of S2, correct? So then I can say that S1 prime satisfies some conjunction over all such successors, right? Like over all such successors S2 prime. Like, so there is some distinguishing formula for every successor. So S2 has all these different successors and S1 has one successor, it is S1 prime. So for each of them, there has to be some distinguishing formula because they are not matching. None of them is matching, right? Then I can take the conjunction of such formulas. So that also S1 prime will satisfy, but no successor, say Sj prime of S2 satisfies this thing, right? So if this is the case, then what happens? Like, then you can have that S1 satisfies, you can construct a formula such that there exists a path such that next of this phi j that S1 satisfies, but S2 does not satisfy this formula phi j. Correct? So if this is the case, then it gives a contradiction that S1, S2, they were CTL equivalent, right? So then it says that, so hence a contradiction. Hence contradiction that S1 and S2, they satisfy the same set of CTL formula. So that was our assumption, right? What we were trying to show is that if S1 and S2 satisfy the same set of CTL formula, then they are bisimilar. Okay. So we got a contradiction that S1 and S2, if they are not bisimilar, then they are not actually satisfying the same set of CTL formula. Okay. So hence, this is we get that if there are two states which satisfy the same set of CTL formula, they are indeed bisimilar. Okay. So now there is one thing here, which is like when we are constructing the formulas here, you see that we are doing a conjunction, and every CTL formula is like a finite formula. So you cannot have, for example, infinite branching from from a state. Okay, so there should be finitely many uh, successors. So in fact, you can show that this direction doesn't hold if you have transition systems which have infinite branching. Okay. So you may not be able to create such a distinguishing formula. The way we arrive at the contradiction is by creating a distinguishing formula. right? If you have infinite branching, then there may exist states which are not bisimilar, but still they satisfy the same set of CTL formulas. So this direction indeed holds in this proof only if you have in the Kripke structure, you have finitely branching Kripke structures. Is it clear? Okay. Okay. Now, what about the other direction? This direction is in fact even simpler. Like, so um, we are trying to show the other direction, that is, if two states are bisimilar, there exists a bisimulation relation between them, then uh, they satisfy the same set of CTL formulas. And this is something we can do by structural induction on the formula, right? So you can talk about the base cases, like they satisfy the same such formulas, and then you can talk about uh, like I mean, you can build up on the formula, right? So what about, like, for example, if your formula is just true, then this is trivial because every state satisfies the true formula. Okay. Um, if it is the atomic proposition, some atomic proposition A, then
so S1 will satisfy only if it's in the label of S1. And so will
exactly, right? So S1, given the fact that they are bisimilar, that means they satisfy the same set of, like the labels should be the same, right? AL of S1 is the same as AL of S2, right? You get from here, this implies that this is the same. That means for every atomic propositions which are here, they are also here. So if this satisfies, there is an atomic proposition A, so S1 will satisfy this atomic proposition if and only if S2 also satisfies that atomic proposition. So for these two, the base cases we have done. What about phi 1 and phi 2? Can you now say this? How do we do for this case? So we are saying the following thing. Suppose S1 and S2 are bisimilar, right? And we are saying, suppose S1 satisfies phi 1 and phi 2. All we need to show that S2 satisfies, S2 also satisfies phi 1 and phi 2. And vice versa. Like if S2 satisfies, then S1 satisfies. But that's quite symmetric. So how would you show this?
because of induction, we know that S1 satisfies phi one if and only if
So S1 satisfies phi 1 and phi 2 if and only if S1 satisfies phi 1 and S1 satisfies phi 2. Okay. Now, so if S1 satisfies phi 1 and S1 satisfies phi 2, and now we have that S1 is bisimilar to S2. Now, since S1 is bisimilar to S2, now you can use the induction hypothesis. Hence, S2 satisfies phi 1 and S2 satisfies phi 2. Thus, S2 satisfies phi 1 and phi 2. Clear? What about exists X phi? We will do exactly the same thing, right? We want to show this. And you will have to use again the induction hypothesis. So can you tell me the steps? So there exists a path, right? Such that uh, in that path, phi holds true, right? So there exists a path such that in the next state, phi holds true. So you should talk about, like, the successor state. There exists some successor where phi holds true. Okay. So how do I go about that?
now you since S1 and S2 are bisimilar.
S1 and S2 are bisimilar, right? So S1 and S2 are bisimilar, and S1 satisfies exists X phi. So that means there exists some successor S1 prime which satisfies phi, right?
There is a successor for S2.
S2 also. and hence S2, suppose I call it S2 prime. So S2 prime satisfies phi because if S1 such that so there exists some successor S2 prime such that S1 prime is bisimilar to S2 prime, right? Because by the definition of bisimulation. And if S1 prime satisfies phi and S1 prime and S2 prime are bisimilar, then by induction hypothesis, you also have S2 prime satisfies phi. Okay. And if S2 prime satisfies phi, that gives you also S2 satisfies there exists X phi. Okay. And you can also do similarly for the globally, let's say. So how do you do that? So S1 and S2. And so now we are talking about, for example, I can talk about a path, right? So we can just think about the path by simulation, that definition, right? So how was it like you have, if you consider the path by simulation definition, like, so for every path, right? Like there should exist a path here. For every path from S1, there should exist a path from S2 and S2 and so on, right? Such that if you now consider one such path, let's say you have a path, um, right? And you can do at like at every position, you have such a mapping like S1, S2, then in that path, this one and this one and this one and this one similarly, right? Such that they are bisimilar. So in each individual state in that path, they are bisimilar. It comes because there was a quantification also on for every path, for all x, if you recall, right? So um, so for all x, wherever you are reaching, they have to be bisimilar. Since it's for all x, for every possible such paths, you can talk about every such pair. Okay. And since uh, they are bisimilar, like so this is bisimilar to this satisfies phi by induction hypothesis, this also satisfies phi, and this just holds for everybody here in the path, right? All of them are satisfying phi. And hence you also get to say that S2 also satisfies, there exists globally phi. Clear? Is it okay? And this is also exactly similar. So you have phi 1 until phi 2, there should exist a path such that you reach some state which will satisfy phi 2, going through states which will satisfy phi 1, and then there should also be something on the other side also which will do this, satisfy the same, and there. Hence, good. Now, this gives us the following thing, that if you have finite transition systems, when I say finite, it you can actually sort of you can generalize a bit more, not just finite, but you can talk about finite branching transition systems. Even if the transition system is infinite, but as long as you have finitely branching transition systems, uh, which without the terminal states, because when we are talking about bisimulation, you always talk about successors, and then you can say that the set of states which are related by these, like satisfying the same set of CTL formulas, they are essentially bisimilar. Like so, this the bisimilarity relation is the same as the relation over the states which satisfy the same set of CTL formulas. And this is for finitely branching transition systems. Okay, so these are also often, sometimes in the literature, they are called image finite transition systems. Image finite in the sense like from one state you can reach finitely many successive states. Okay, for image finite transition systems, this holds true. And okay, now, there is one thing then you can, as a corollary, immediate corollary, you can get is like if there are two states which are not bisimilar, then there should exist a CTL formula which that distinguishes them. Correct? Right? So you have these two, let's say, Kripke structures. You look at these two states, S and T. Now you ask the question that if they're, say, yeah, Kripke structures are K1 and K2. Now we have seen that they are not bisimilar, right? We have seen that they are not bisimilar. They are trace equivalent though, but not bisimilar. So can you say what is a distinguishing formula for these two Kripke structures? What is a distinguishing formula?
Uh, Globally, there exists a path to B.
So a formula in CTL, it should start,
Yeah.
cannot be a path formula. It has to be a state formula, right? So
Yes. Yeah. For all, like it's for all G, there exists GB.
for all G, for
Uh,
paths globally,
like eventually there is a B. No. Yeah. Because in K2, let's say if you're in T2, you can't reach B. So that is the distinguish.
so can you say again?
For all globally, uh,
Yes,
actually, there exists eventually B.
there exists FB.
Yeah.
For all paths, it is always the case.
Oh, okay. No, this doesn't work actually because you can be in C and
Exactly.
yeah, yeah,
So because certainly this path doesn't satisfy.
yeah.
We could see like some for formula satisfying K2 and not K1, there exists a path
There exists a path.
such that eventually not C.
There exists a path such that eventually not C. But
Oh wait,
there exists a path
such that next of eventually not C.
there exists a path such that
No.
x of
No. I just I think for all globally there exists eventually.
so what would you like to say?
Like
Uh,
I want to use the fact that once it goes to S1, like okay. Not really.
We can just say for all next, there exists next C. Just
One second. So sorry, you were saying something.
Like from S1 we can see B and C both.
B and
from
C both,
T1,
exactly.
We can only see B from T2. We cannot see-
Exactly, yeah. So how do you write that? From S1, you can see both B and C. That's the difference,
Yeah.
right? Which you cannot do here. So what is the, how do you write that?
For all globally. Even next should be.
Yeah, okay.
Yeah. For all,
So from S1, so essentially you can reach somewhere where there is S1 from which you can see both.
oh yeah. So for all next state, there exists
Okay. So you are saying for all
for
paths,
paths.
it could have been a there exists also because just there is one path. But anyway, go ahead.
No, but then we can take the correct K2, yeah. Correct path, right?
No, I mean, I'm saying that there exists a path. There exists, I mean, okay. So first of all, I'm saying that the formula I'm going to write will be satisfied by this one.
Yeah.
K1. So which says that there exists a path such that I reach here from where both the things can be satisfied in the next step. Right? So that way I'm saying there exists could have done also. But anyway, go ahead.
So the next one should have a successor which satisfies B and a successor which satisfies.
Yeah, okay. So how do I write that?
For all, next,
Next.
there exists, exists as that next B and there exists next C.
Good. There exists next B and there exists next C. Okay. Along all paths, okay, along all paths, I can go to a state from which there exists a path such that, so along all paths, so you have fixed the path. Now you go to the next state where from there you can satisfy both B in one step as well as there exists another path in along which you can see you can satisfy C in the next step, right? So this is fine. So all I was saying is that this is good, but everything works. This, I mean, whatever you have said is fine, but I'm saying that if you just say this is also good. This is also good. And why I prefer the existential, because the reason being it kind of matches with the move of the challenger. Like, so see, if there is a challenger and then there is a defender. So the challenger is choosing something and the defender is trying to match. Now, when will the defender lose? If the defender cannot mimic what the challenger is doing. So the challenger chooses something, like there exists something, like that this is what the challenger does. There exists something, but the defender is not able to match that. So the direction which the challenger is doing something, there is an exists quantifier there. Okay, and there is something that the challenger can do. So this particular Kripke structure will satisfy that, whereas the other one is not able to do that. Okay, so if you just follow the moves of the challenger and the defender, you can actually construct such a formula, right? You can construct such a formula. Okay, if the challenger has to switch side, if the challenger has to switch side, suppose you start from one side, like, so you are trying to build a formula, let's say for this Kripke structure, this side which the challenger starts from in the very beginning. But maybe it can happen, like as I was saying, that you can try to construct Kripke structures, okay, where the challenger may need to actually switch side in order to win in the middle of the game, some configuration, right? So you should try to think of such Kripke structures. I mean, these are things I may give, for example, in an assignment or an exam and things like that, okay? So now if the challenger switches side, now it will be like a there exists from this side, right? But now if you look at this from this side, it's like then it's like it becomes like a for all with respect to this, because it becomes like a there exists from this side now because the challenger has switched side and then there exists something, and this is equivalent to like a for all along this from with respect to this Kripke structure, right? Do you see? So I'm saying that if the challenger starts from here, then you say that there exists something. This is something, there exists a path along which the challenger can do something. So this is what will be satisfied by the Kripke structure, the formula that you will be constructing while following the moves of the challenger, right? Now you are saying that so on the other side, if you say that, okay, you want to have a formula which the defender will satisfy, then it should be the negation of that formula, right? So the negation of there exists is like for all. Okay, so the defender can do is like, if I'm saying the challenger does there exists, the defender is going to do something like a for all. The negation of that formula is something that this guy will satisfy. Okay, this guy does not satisfy the there exists something. So this guy will satisfy the negation of that, which will bring a for all. Okay. Now, when the challenger moves to this side, let's say, and does a there exist from this side, then this guy has to satisfy a for all corresponding to that. Does it make sense? Is it clear? Right. So if you start with like this, so it is not going to be always there exists corresponding to one side. There may be some for all also. So in the formula, there can be some quantifier alternation. Or instead of writing a for all, you can also write a negation of the there exists. Does it make sense? Like if you don't want to use for all, if you're writing the formula in an ENF, existential normal form, you can put a negation there. Okay, so you can actually construct the formula by playing the game. If the challenger wins, which means that if they are not bisimilar, then the challenger has a winning strategy. And following the strategy, the moves of the challenger, you can actually come up with such a formula, distinguishing formula. Is it clear? Right? I mean, when there will be a for all and when there will be an exists. You will actually get to see a quantifier alternation in the formula if the challenger has to make a switch from one side to another. Okay, right. Good. So this is some formula which the K1 satisfies this formula, but K2 does not satisfy the formula phi or okay, good. Now, in fact, you can see that if the challenger moves and suppose the challenger wins, okay, then the challenger is going to win in a finite number of steps. Okay, the challenger is going to win in a finite number of steps. Let's say some 5 steps, maybe 2 alternations in those 5 steps, right? So you can in fact construct a distinguishing formula just by let's say these atomic propositions. We have seen atomic proposition. We also have in the distinguishing formula conjunction, right? And I can use, let's say, negation, as I was saying, that if the challenger switches side, and you don't want to use for all, but you can use a negation in that case. Okay. And the other thing is that you can use such exists X, right? You don't really need to use the until formula or a globally, because it's only in finite number of steps the challenger is going to win. And you are going to get a distinguishing formula of that size, right? Which will capture the alternations and the number of rounds of the challenger, right? So all I'm saying is that, in fact, the distinguishing formula can be with respect to this exists X, negation, conjunction, and atomic propositions. So you can even have something like a tighter sort of like a theorem which says that if they are bisimilar, then they satisfy all formulas which will be using only these operators. You don't need to talk about really the other things like the until and the eventuality, globally, etc. As long as they satisfy these operators, all formulas which only use these operators, they are bisimilar, same set of formulas with these operators. Is it clear? Right? And on the other hand, like you can also talk about like if two things are bisimilar, two states are bisimilar, they also satisfy the same set of CTL star formula, not only just CTL. Okay. So we looked at two directions, right? So when we talked about bisimulation and CTL, we talked about two directions. It's like this implies they are bisimilar. The other was like in this direction that they satisfy. And for this direction, we also mentioned that you need the image finiteness, right? We also need the image finiteness. Now, if you talk about CTL star, then which of these implication directly holds? If you talk about CTL star instead of CTL, so I'm talking about this. And now I already have these two proofs. Which direction directly holds? CTL star implies bisimulation because you have now more formula. It's even a stronger thing. You are saying that they satisfy the same set of CTL star formulas, right? And hence, if they satisfy like the same set of CTL formulas, they are bisimilar. If they satisfy the same set of CTL star formulas, they will also be bisimilar because you have now more things here. So the important thing is this direction, right? The important thing is this direction, which is actually not very difficult. I mean, what we used for this direction, we used the structural induction. We used structural induction here, right? For this direction. And for CTL star also, you can just use the structural induction in the same way. The proof is not very different. Like now, earlier you had those alternations of like formulas in CTL, like you have the state formula, path formula. Now you have everything on the path formulas. You can have the conjunction, disjunctions, even on the path formulas, and but pretty much the same idea. The proof is not very different and it holds true, right? But what is interesting is actually this part that if they are not bisimilar, then you can actually find a distinguishing formula in this fragment. Okay. And in fact, like if they are bisimilar, then even if they are just satisfying these formulas, which use these operators, same set of formulas using only these operators, then they are indeed bisimilar. Okay, good. So, okay. So now we will talk about something called binary decision diagrams. Okay. So binary decision diagrams or BDDs, they were introduced by somebody called Randall Bryant from CMU. So and essentially like BDDs are hugely, I mean, they're very widely used for verification of hardwares and things like that. And this paper on BDDs, which he wrote, I think, I don't exactly recall which year, 81 or 86 sometimes. It's one of the most highly cited papers in history of computer science. Okay, so what is a binary decision diagram? I mean, it's like a decision diagram. We'll see what a decision diagram means, which captures essentially Boolean functions. You know what a Boolean function is, right? Like it's a propositional logic formula, right? So a Boolean expression, for example, it's of this form where you have like a variable x, and then you have the true and like the false and the true, 0 or 1, false, true. Then negation, conjunction, disjunction, implication, by implication, etc. You can also have these priorities, right, for these different operators. Then you can talk about satisfiability. Essentially, like you have a Boolean formula, it is satisfiable if some valuation makes it true, the formula true. And tautology is like every valuation would make it true. That is tautology. Okay. And then you can say negation and disjunction. These are functionally complete. So any Boolean function, you can just use this negation and disjunction. Okay, and there are certain normal forms, like one is a disjunctive normal form. So what is a disjunctive normal form? What is a disjunctive normal form for a Boolean expression?
Like it's a bunch of R's, and in each of the things there's an and.
Yeah, so you have like something like x1 and x2 and something like this, and it's of this form, right? And you can also have negation of such variables. So this is called a literal. Okay, so a literal is either a variable or a negation of a variable. A variable or negation. Variable. Okay, so this is disjunctive normal form. And similarly, conjunctive normal form, you have something called, these are the clauses you have. Like here, there are disjunctions in the clauses, and then you have conjunctions. So this is conjunctive normal form. Okay, so you call them like DNF and CNF, and any Boolean expression you can always convert them into CNF and or in DNF. Okay, any Boolean expression can be converted into CNF or again, I mean, same thing, any Boolean expression can also be converted into DNF. Into DNF. Okay, you can do this. Right, and now however, from CNF to DNF, when you are translating, then it can lead to an exponential growth in general. One normal form to another normal form. So there are certain advantages of each of these normal forms. So for example, like if I talk about satisfiability, satisfiability checking. Okay. So which one would you like to use? Do you want me to give the formula in CNF or in DNF? DNF. Why?
Because then we can just look at each of the clauses.
Each of the clauses, yeah, which is a conjunction of things.
And since it's a conjunction, we just have to check if everything.
Check if what?
Actually, I both of them. Oh no,
So I'm talking about satisfiability. There exists some valuation which it.
oh yeah,
It
so
is.
it's like some clause which doesn't have x1 and negation of x.
It should not have x1 and negation of x, right? That is all. So as long as you find some clause which doesn't have a variable and its negation, right? As long as there exists some clause, you know that this is satisfiable, right? It should not have both the variable as well as its negation, right? So you can indeed do it. If it is given in DNF, then you can do it in linear time. Okay, clear? Now, what about tautology checking that whether it is true for all valuations? How would you do that? Whether it is true for all valuations. So that means that in C, okay, if you consider CNF, then everything has to be true. Everything has to be true.
So its negation should not be satisfied. And its negation will be in the disjunctive.
Okay. So
tautology checking should be easier for the CLM.
yeah, so all you just need to do here is that, like for each of the clauses, right? All you need to do is that each of them is true, right? And when will each of them will be true? It's like each clause should have a variable as well as its negation because they are in disjunction. Okay, there should be some variable and a negation of that variable in every clause. Okay, if that is the case, then it's true. It evaluates to true. Okay, so indeed, this is good for CNF. Okay. Okay, so now we will, for the purpose of BDD, we'll look at another normal form, which is called the if then else normal form. Okay, so the idea is the following: that you do a check on the variables, right? And you may do the check on the variables in certain order. So suppose you have four variables x1, y1, x2, y2. So you can choose an order. Let's say first you would check whether x1 is true. Then you would, if it is true, then you will do something. And then maybe you will check whether y1 is true. If y1 is true, then you will do something. Like when I say do something, it's like we are trying to build a decision diagram. We'll go to different branches based on whether the value is true or false. Okay, so suppose this is x is here. It essentially means that if x is true, then we'll consider y0. If x is false, then we'll have y1. So essentially we'll say if x is true, then y0 has to be true. If x is false, then y1 has to be true. That is what it essentially means. It's like a decision tree. So it depends on the value of the x. Whether x is true, then I'll say y0 has to be true. If x is false, then y1 has to be true. Okay, so we have t arrow t0 t1. It means that if this is true if both t and t0 are true, or if t is false and t1 is true. Okay, so for example, like if you consider any Boolean expression, you can write this in the form of uh, such if then else operator. Okay, so for example, if I consider negation of x, it's a Boolean formula. So I'll say if x is true, then it has to be false. The negation of x has to be false. Okay, on the other hand, if x is false, then the negation of x has to be true. Okay, this is fine. So similarly, how do I write just x? If x is true, 1. If x is false, then it's 0. How would I write x is equivalent to y? So suppose here the thing is that I can put some order on the variables. Okay, the order in which I am going to check them. Okay, first maybe x or first y, and then if I first choose x, then next I'm going to choose y, and so on. Okay, so if x is equivalent to y, so what by x by implication y? So what am I going to do?
If x is true, then y.
X is true, then
Y.
Then why?
if x is true, then if y is true, then I'll choose y. Okay. Then if y is true, then it is 1, otherwise 0. Else, if again y, if x is false, so if x is false, then I go to this branch. Then if y is true, then I'll have 0. And if y is false, then I'll have 1. Okay. So this is the for x equivalent to y. What about x or y? How do I write this?
X goes to y.
If x is true,
Then y 1.
if x is true, then I will have just 1 because x is already true, x or y. If x is false, then I'll talk about y. If y is true, then 1, otherwise 0. Okay? So that's the thing. Okay? So the if then else normal form, it's a Boolean expression. So you have this is built entirely using this if then else operator. So you have the constant 0 and 1. And you have the tests are on the variables. Okay, so this is the thing. And now if you are given an expression, a Boolean expression t, so I will denote by t0 for x as the expression where x is replaced by the valuation 0. Okay, so this is t0 for x. And similarly, t1 for x denotes the Boolean expression which is obtained by replacing x with 1 in t. Okay. So now there is something called a Shannon expansion, which is like, so sometimes this t0 for x, we are also going to write this as t0, and here it may be like t1. Okay, so it's like maybe sometimes what will happen is like if you have variables x, y, z, so I'll say t001 to represent that x is given a value 0, y is given a value 0, and z is given a value 1, and so on. Okay, so this is just a notation. And the Shannon expansion, it says that this is this one which has variable x. So if x is true, then it's like you can write it as t1 for x, comma, if x is false, then t0 for x, right? So I can also write this in the form like x to t1, comma, t0, like this, okay? And you see that this expression and this expression t1 and t0, or t1 for x, t0 for x, so they have one variable less than the expression t. They have one variable less than the expression t. And you can just do this recursively. Now you can have more variables and you can again just recursively expand. Okay. So, yeah. So that is, so if t contains no variable, then it is just like either true or false. If the expression doesn't have any variable, then it is just an expression corresponding to true or false, just one or zero. Okay. And if you have t has more variables, then t1 and t0. So t1 and t0 have one less variable than that of t. Okay. So far it's just Quite simple. Now, I mean, as I was saying that any given Boolean expression, you can write this into an equivalent if then else normal form. Now, suppose I give you such, just look at another example. Suppose I give you one Boolean expression which is of this form. X1 is equivalent to Y1 and X2 is equivalent to Y2. And you choose a specific ordering of the variables, X1, Y1, X2, Y2. Okay. So now suppose this is my T and I can say my T is of this form. Like suppose I say X1 and I write, let's say T1, T0. Okay. And how can I write T0? Now I will talk about Y1. I will make the decision based on Y1. So if Y1 is 0, then what do I so if Y1 is 1, then what do I write here?
Oh, T0.
If Y, yeah. So I'm just expanding T0. What is T0? Where T0 you have set X1 to 0. Okay. X1 is set to 0. Now in T0 I am setting Y1. Y1 can either be 1 or 0. So if Y1 is set to 1, then you are going to get 0, right? And if Y1 is set to 1, then I'm going to look at both X2 and Y2 again, right? So I'll then say this is T00, okay? T00. Clear? If both of them are equal. What about T1? So now if
What is T00 here?
so T00 corresponds to like X1 is set to 0 and Y1 is set to 0. It's the expression T, it's the original expression T, where both X1 and Y1 are both set to 0.
Okay. And if Y1 is true, then it is 0 because, well, the first clause is not satisfied.
Yeah, because there is a conjunction here, and Y1 is set to false, whereas X1 was so X1 was false and Y1 was set to true, right? Y1 was set to true, whereas X1 was set to false. Hence, this is, they are not equivalent, hence it is 0. Right? So I write 0. Is it okay?
Yeah.
So what about T1? What about T1? If Y1 is now set to true,
So T1, we should check.
if Y1 is set to true, then T11. If Y1 is set to false, then I have 0. Clear? Let's write now T00. Right?
This
So I
is
have
equivalent to
X2.
T1.
Huh?
This is equivalent to T1.
This is equivalent to
T1.
T00.
Because in both cases, we just want to check for satisfiability next to definitely.
So if in yeah, exactly. You are right. You are right. Exactly. Indeed. Okay. So T00. So if I now talk about X2, then what do I have? If X2 is, let's say, true, then I will talk about T001. If X2 is false, then T000. Okay, so far it's like this. And let's say we have T11. Similarly, if X2 is true, then I have T111. And if X2 is false, then T110. Okay. And now let's see what is T000. Okay, so T000, I have to talk about Y2. If Y2 is true, then it is going to be false, right? If Y2 is going to be false, then I'll have 1. Okay. Similarly, T001. If y2 is true, then I'll have 1. If y2 is false, I'll have 0. Okay. And let's say I also have these two. Let me just try to make some space. So now I have what else? T110. If y2 is true, then I'll get 0. If y2 is false, then I get 1. And T111, if y2 is true, then I get 1. If y2 is false, I get 0. Okay. So now let me try to draw what is called is the decision tree corresponding to this. Okay. So essentially I'll have the variables x1, y1, x2, y2, and I'll see that how they look like. So if I have x1 here, then suppose if I set x1 to true, I'll check y1. And now suppose if y1 is set to false, so I write the false using such a branch. It's called the low branch. And this is called a high branch where you set it to true. That is called a high branch. Where you set it to false, it's called a low branch. Right? So high branch is like in solid line, and then the low branch is in dotted line. Okay. So then you directly come to the 0 node. Okay. On the other hand, if it is true, then you will check for x2, right? In the ordering we have. And if you have, let's say this is true, then I'll check for y2. And if y2 is also true, then I'll go to this branch 1. Okay. And if y2 is false, then I'll go to a 0. Okay. Similarly, here also, if x2 is so if x2 is false, let's say, then I'll go to again y2. And if y2 is false, I'll go to 1. If y2 is true, I'll go to 0. Okay. And similarly, I can also do it for the other direction. Like if x1 is false, then you talk about y1. And if y1 is true, then I'll go to 0. If y1 is false, then I'll talk about x2. And if x2 is true, then I go to y2. And if y2 is true, I'll go to 1. If y2 is false, I'll go to 0. Okay. And if x2 is false, then also I have y2, and y2 is also false, I'll go to 1. And if y2 is true, I'll go to 0. Okay. So this is called a decision tree. You call it the decision tree. Okay. For this Boolean expression. Now you see that in this decision tree, in fact, when we look at, let's say, these two here, like T001, let's say T001 and T111, they are the same, right? And similarly, T110 here, this is the same as this T000. Clear? So essentially, I think, so which corresponds to T001? So 001 is this thing, I think. This is T001. And similarly, you can also talk about T111, which I think is this one. Okay, so these two are the same. So now when we draw the decision diagram, what we do is like first we would merge such nodes which are the same. So for example, like for all the zeros and the ones, the terminal nodes, we will just have one node for 0, one node for 1. So we are not going to have a tree anymore. We are going to have a DAG. Okay. And similarly, these two we can merge. And then T110, let's say, which is like 110 is this one. Okay. And T000, which is like these two, we can merge. Okay. So if we do that, then so we have the T000 and T110, right? So these two are going to be the same. And similarly, T000 and T111, they are, okay, sorry, T001 and T111, T001 and T111, these two are also going to be the same, right? So you see that in that case, both T00 and T11, they also become the same, okay? So, okay. So if I just do this, so I can say that this is like T00, I can just write it in this way. That here, instead of writing this, I can write T001, comma T000, and here I can write essentially this. So my T00 and T11, they become the same, and I can merge these two. Okay, so they are essentially the same thing. And right, so if we identify all these equal sub-expressions, so once you identify the equal sub-expressions, we obtain a DAG. And this is called a binary decision diagram. Binary decision diagram. Okay, it's no longer a tree. So now if I look at, let's say, this thing, so what all do I get? So I'll just write this, and let me just write what we get here. So I'll have the T, which is of the form T1, T0, then T0 I will have 0, then T1 I'll have, right, because these two become the same, T00 and T11 are the same, so I'm just writing here T000, sorry, T00, and now T00 is the same as x2, T001, T000, and okay. So you see that now I have reduced the number of nodes here, right? So what the thing that I'm getting is like this. I have x1, and on the low branch I have y1, and here if so I'm here x1 on the low branch, I am here on y1, and if y1 is true, then I get a 0 directly. Okay, And if x1 is true, here I see y1. And so in T1, if y1 is false, I get to 0. If T1, y1 is false, I get to this 0, right? So I take the low branch and I reach here. And similarly, I can have, there is a low branch. If y1 is on the low branch, I go to T00 here, right? So it is T00. T00, you are checking on x2, okay? And if x2 on the low branch, I'll go to y2, right? So this corresponds to this T001. Here I have y2. And if y2 is
That corresponds to T0000.
oh, sorry, this is T000. Right, you are right. So this is T00, and if y2 is true, then I get to 0. Okay. So if y2 is true, I'll get to 0. Clear? And if y2 is false, then I'll go to 1. Okay. And here, so x1 and y1, if I have, for example, let's say x1 and y1 is true, so I go to T1, and T1, when y1 is true, I go to T00, okay, where I am checking on x2 again. Okay, so if I have x2, and here if x2 is x2 becomes true, then I go to T001. So if x2 is true, then I'll go to y2 T001. And if y2 is true, then I come here. Otherwise, I'll go to this one. Okay. So this is the binary decision diagram. So earlier we had so many nodes. Now we have reduced the number of nodes here if you make it a DAG. Okay. And it's called an ordered BDD if the variables are the same in the same order along all the paths, right? So what we have drawn is indeed an ordered BDD because you are checking the variables in the same order.
But not all the paths have all the variables.
That is okay. All the variables may not appear on all the paths. Okay, so essentially when you say that a variable actually doesn't appear on the path, it means that the low branch and the high branch of that particular variable, they go to the same node. Okay, so if both the low and the high branch are going to the same node, you can actually get rid of that variable. Okay, so now what you call a reduced order BDD is essentially, you can see that exactly what you were saying, that some of the tests may become redundant, and which we would remove, right? So that is, I mean, an ordered BDD is essentially like along all the paths, you have the variables are there in the same order. But now, I mean, we have already actually reduced some of the nodes here, which is like a reduced order BDD, in the sense that one of the things is that like some of the tests are redundant in the sense that the low and the high branch, if they go to the same node, then you don't need to have that test at all, right? So that one can remove, uh, right? The second thing is like, so essentially if both high and low branches go to the same node. So this same node, such redundant tests you can remove. And the other thing is that like if there are two nodes, I mean, for example, two nodes, U and V, such that high of u equals high of v, okay, and low of u equals low of v, and they both have the same value. They both, I mean, both u and both u and v, both u and v test the same variable, then merge u and v. Okay, so you are doing such a thing. So then what you get is a reduced ROBDD. So often when people talk about BDDs, they mean is the ROBDD, reduced order BDD, ordered BDDs. So here are some examples. Like, so if you consider the BDD for just true or one, you can have this, or you can just talk about like the x1, and then you have the x2, and x2 has this high and low going to the same thing. If that is the case, you can remove the x2, and then x1 directly comes here, the low branch as well as the high branch. So you can also get rid of the x1. Okay, so these are all BDDs for one, but this is the ROBDD. Okay, and the BDD, if you consider x1 or x3, you can indeed just have like the low branch. I mean, if I have to write for x1 or x3, an ROBDD will look like this, that if you have the 1, then this is 1. If you have 0, you talk about x3, and then this is the 1. If this is false, then you have 0. This is how it should look like, right? Whereas, yeah, here you have some redundant tests on x2, which we would like to remove. Okay. So in the BDD, then what we have are like the terminal nodes, which are the zeros and the ones. Terminal nodes 0 and 1, and you have some non-terminal non-terminal nodes which have degree 2, right? They will have degree 2. These are the internal nodes. So I talked about what is an ordered BDD. Along all paths, the variables on which the tests are done, they have the same, or they are in the same order, and an OBDD is reduced if there are two things. One is like, as I said, that the nodes should be unique and there should not be any redundant tests. So this is like an ROBDD. Okay, so these are some examples where such things you do not allow. For example, like you cannot have y and z, like both of them should test after x the same variable. The order should be maintained. And such things are also the should not be allowed, like you should not have two different nodes with the same label and same tests going to the same successor nodes, and such non-redundant tests should not be there. Okay, so this is about the ROBDDs. And now one of the important things about ROBDDs are like, so if you consider any Boolean function, a Boolean function, let's say, which is of the form this, right? So it's like n variable Boolean function, and there is exactly, and you fix the order, okay? Fix the order of the variables, order of the variables. So there is exactly one ROBDD representing the function, the Boolean function. Is it okay what it says? So if you have a Boolean function, if you fix the variables, the order of the variables, then you are going to get exactly one ROBDD. Okay, exactly. And as a corollary, you can see that there is exactly one ROBDD for the constant true and constant false. right? So for example, like if you are given a function and if you are asked whether it is a tautology, if you have the ROBDT form, then it's a constant time operation, checking that. You just have the node 1 corresponding to a tautology, right? So having a BDT checking whether something is a tautology is just a constant time operation. Okay, similarly, whether if it is a false always, it's just a constant time operation. Okay. Yeah. And yeah. And that is the thing. What else? Okay. So I'll just talk about this canonicity lemma, which is what we discussed. For every function f from which is a Boolean function over n variables, there is exactly one ROBDD, which is this u. The BDD itself, I'm calling it u. And if you are fixing the variable ordering x1 to xn, such that I mean this is essentially the ROBDD. It denotes a function over this variables x1 to xn. Okay, so there is just exactly one ROBDD. So what is the idea? Like you can do it for the best cases. I mean, you can do it with the proof is quite simple. I mean, just do an induction on the number of variables. So if you have no variable, then it's a constant true and false, for which you have seen that you have just one ROBDD. The true is like one node which has a 1, the false is one node which has a 0. And then suppose if it holds for uh, essentially like n variables, and then you have, let's say, you have variables of the form, let's say x1, x2 up to xn plus 1. And suppose you have got uh, some f, let's say b of x2 to xn plus 1. So this essentially denotes that the variable x1 is set to a value b, right? So this is like this. And now you can talk about like u0 corresponds to the ROBDD where the variable x1 is set to 0. u1 corresponds to the ROBDD where the variable x1 is set to 1. So you have these two ROBDDs, and all you would have now is test x1, and then you would go to the ROBDD u0 and sorry, here u1 and u0 like this. Okay. Now, if it is the case that both of these u0 and u1, there can be two cases. Either u0 and u1 are different or u0 and u1 are the same. If u0 and u1 are the same, that means that the value of b really doesn't matter. Then you have like f of 0 x2 to xn plus 1 equal to f of 1 of x2 to xn plus 1, right? In which case you have the same ROBDD for both this as well as this, and you can just get rid of now, since both of them, the high and the low branch, they go to the same thing, you can just get rid of this, and essentially u equal to u0 equal to u1, right? If both of them are the same. If they are different, then you will have such a thing, okay? And indeed, now you can say that suppose this ROBDD I call u, and suppose there exists a different ROBDD which is of the form v, which is different from this u. But then you can argue that the v will be exactly the same as u because the variable ordering is fixed. So first you will check the value of the variable, test the value of the variable x1, and depending on the value will go to either u1 or u0, and essentially they are the same ROBDDs. Okay, so the ROBDDs for a given Boolean function, it's the ROBDD is unique. Okay, so this is what this canonicity lemma says. Okay, so any Boolean function you consider, if you fix the ordering of the variables, then you get a particular ROBDD. Now one can ask the question that what So I did not go over the details of the proof. You can pretty much, and this is a broad idea, but I think you can construct. Now, one question is that what, so we were working out this particular Boolean function, right? The ROBDT corresponding to this, where we had like this was the ordering what we did earlier. X1, then followed by Y1, X2, then followed by X2, followed by Y2. So this was the ordering we had. So essentially X1, Y1, X2, Y2. Okay. And how many nodes we had here is like, if you discount the 0 and the 1s, like 1, 2, 3, 4, 5, 6, 6 internal nodes in the ROBDD. But now if you change the order, so what was the order? X1, Y1, X2, Y2. If you change the order to X1, X2, Y1, Y2, right? So this is the new order I'm talking about. Earlier we had X1, Y1, X2, Y2. We had 6 non-terminal nodes in the ROBDT. Non-terminal nodes in the ROBDT. If you now change the order to X1, X2, Y1, Y2, then you see that like you can try to work it out. You have here 1, 2, 3, 7, 9 non-terminal nodes. Non-terminal nodes. So the canonicity lemma, in fact, talks about that given the Boolean function as well as the, once you fix the ordering, then the ROBDT will be unique. Okay. So in fact, the size of the ROBDT may drastically depend on the ordering of the variables. Okay. So if you, so it's important that when you are given a particular function, you are constructing the ROBDT. In practice, it's very important that you somehow choose the order in a way such that the size of the ROBDT is small enough. Okay, good. So I think I'll end here, and in the next class, I'm going to talk about like how we use these things, these Boolean functions in actual verification or model checking. How are the Boolean functions used, right? We are going to look at CTL model checking and see a symbolic way of manipulating the states or do for the purpose of verification, CTL model checking. Okay, and where we will be essentially representing the states with the help of such Boolean functions. And it will be a succinct representation, and that is called a symbolic model checking, because we are doing the model checking with the help of some symbols, which are these variables. Okay. So that's the idea. So for example, like if you say that you have, let's say, 4 states, okay, and you want to consider some subsets of the states. So suppose if there are 4 states, like you can encode them with 2 variables, like 0, 0 is state 1, 0, 1 is state 2, 1, 0 is state 3, 1, 1 is state 4, 4 states. And you can, now, if you just want to talk about state 1 and state 3, you can just talk about the state 0, 0 and the state 1, 0, right? So this set you can represent using a Boolean function, correct? Like, so for example, I'm saying that 0, 0 and 1, 0. These are the encoding of 2 states, right? So I can represent this using, let's say, if I'm using 2 Boolean variables, 2 bits, x1 and x2, then this is like saying that negation of x2. Okay, the negation of x2 can represent this set. Is it okay? Is it clear? Like the value of x1 here doesn't really matter. The value of x2, the negation of x2, it may represent this set. So that is the idea. Like, so now you can represent this Boolean function with the help of the BDDs, because they will be small representation. And you can also do all the transitions, like when we are doing CTL model checking, like suppose we are saying whether a particular state satisfies the formula of the form exists next 5, right? And we saw how to compute such sets of states. given, like we talked about this, the parse tree of the formula, you solve from the leaf nodes, and then you go up the tree to compute the sets of states, right? Now we are saying that we will represent these sets of states using such Boolean function, okay? And then we will be doing our operation on these Boolean functions, which will be represented as ROBDDs, and to compute the sets corresponding to satisfying such formulas. So that is what is called as the symbolic model checking. Symbolic model checking. Okay, so we'll just do this, and I think that should end the verification part. It's okay, and then we'll talk about games in the last 2-3 lectures. Okay, so any question? Okay, so let me then stop the recording.